So a very good evening. Uh, in today's discussion session, we will be discussing on the accelerated pre-consolidation techniques. That are the sand drains, the prefabricated vertical drains, and then the vacuum-assisted pre-consolidation. All right, and after that, we'll be studying about the stone columns and water. We will be learning water encased stone columns and how encasement of stone columns is actually beneficial, right? And after that, and we will be solving some problems from some of these topics. Okay, so in the previous class, we had solved problems where we used geosynthetic reinforcement to increase the uh, bearing capacity of foundations. Okay, so we specifically solved a problem where we use reinforcement to increase the bearing capacity of strip footing, right? And we also saw that how changing some parameters changes the design, and actually we have to do some trial and error to get the perfect solution. So for DC calculation we had actually used Excel for the purpose, so we solved those things. And now today we will be seeing the next topic, that is the pre-consolidation technique and stone columns. And after that, in the next class, we will be seeing some other uses of geosynthetics, that is other minor uses. Those are filtration and all those things, where the geosynthetic is actually used as a filter. Okay, and also where the geosynthetic is used as a drainage system. Right, so we'll be solving some short problems regarding that. So those problems are actually quite easy, so we'll be solving those problems in the next class, in the next discussion. So only some of the only how much today is the ninth, so ninth, 10th, so we are ninth. After ninth, so only three more discussion sessions will be there, and we will have one 13th discussion session that will be just half an hour, sorry, 1 hour long, where we will revise, just skim through, we will just skim through all the topics from the first week to the 12th week. Okay, that we will help, say 1 or 2 days, probably 1 or 2 days, just within a 1 week time. Okay, within 1 week of the 12th week lecture. Okay. All right, so mainly primarily we will be having three more discussion sessions after this nine. So 12 discussion, live discussion session, and also we'll be having one 13th summary session where uh, re- we'll be like just summarizing whatever we have learned in this course in this 12th weeks. Okay, that summary session won't be 2 hours long, it will be just 1 hour long. So in those 1 hour we'll be trying to actually summarize okay. So yeah, so today is 26th, so after this the next discussion session as usual will be on 3rd, then 10th, then 17th will be the last discussion session, and after 17th we will have one more discussion before 24th, around 24th October. That will be on that will be a summary session of 1 hour, 1 hour duration. Okay, so total we will be having 13 sessions, 12 12 these problem solving discussion sessions and one summary session. So let us start. Okay, so what are sand drains actually? So sand drains are used for accelerated pre-consolidation. So pre-consolidation means what? Say you have a land. Okay, you have an area, you have a land, and above that you need to construct something. Say you need to construct a flyover or a building or some large tank to store oil. So there may be many reasons. Okay, but so what happens is that the soil over which you need to construct it, when you calculate do your calculations, you found out that the consolidation is actually going to take a lot of time. Okay, the consolidation will actually be taking a lot of time. So in order to accelerate that consolidation, we use this pre-consolidation technique. So what we do, we uh, keep some pre-consolidation pressure over that area in terms of this surcharge. Okay, say in terms of this surcharge, we'll give some pre-consolidation pressure, and so that there is consolidation, so that consolidation takes place before the construction. Okay, so to accelerate that process, what we do, we can use many techniques. So one of them is sand drain. So sand drains are what? Sand drains are the cylindrical drains that are drains made up of sand only, made up of sand columns that are constructed into the soil, into the land, so that the drainage path of the liquid is reduced. So if the drainage path of the liquid is water is reduced, what will happen? The pore water pressure dissipation will be faster, and as the pore water pressure dissipation will be faster, the consolidation process will get faster. So say previously for 90% consolidation we would have required 10 years. Now for 90%, now we can achieve 90% consolidation say within 9 months or 1 year. Okay, so that is the main purpose, to accelerate the consolidation, so that all the consolidation happens faster. Okay, early, so that after we construct whatever structure we want to construct, there is minimal settlement. So if there is high settlement after the construction or during the construction, what happens, there are chances that the structure will fail due to uneven settlements. Okay, so in order to prevent that, what we desire that maximum consolidation should occur before it. Alright. So for that purpose, we use this accelerated pre-consolidation methods. One of them is sand drains. Okay. So what happens? Drainage paths are reduced, and the dimensions of sand drains are also given. You can see 200 to 600 mm in diameter. They are cylindrical, and they should be at least 1,000 times more permeable than the native foundations. Okay, and so this specification of this blanket, okay, this blanket soil which will act as a drainage path. So water will actually come from here, enter this sand drain, go above, come here, then drain out. Okay, then drain out like this. So whatever this blanket soil actually should be more permeable than the sand drain to drain away the water coming from the ground. And the thickness should be about 300 mm. Okay. Now the equation that you see next, that is the equation for the three-dimensional part, 3D consolidation equation. Okay, 3D Laplace equation actually. Okay, there is nothing but the 3D Laplace equation where this U is the pore pressure. So dou square x square plus dou square u by dou y square into CH. This is what? This actually is the radial. This will define this radial flow of water. Okay, this radial flow of water. Okay, this radial flow, and this cv times dou square u by dou z square, that will define the vertical consolidation. Okay, and that equates to dou u by dou t, that is the change in pore water pressure with time. All right, so as this defines this radial flow, you can see this horizontal or radial coefficient of consolidation here, and with this term you can see this cv is nothing but the particle consolidation coefficient of consolidation. All right, so from here actually, so here you can actually get this ur, capital ur and capital U and small u, do not confuse. Small u is the pore water pressure, capital U represents the degree of consolidation. Okay, so capital ur actually you can get, so capital ur is what? Is the degree of consolidation due to radial drainage, and uv is the dV is the degree of consolidation due to vertical radius. Okay, so when we combine this, actually we can get the average degree of consolidation. Okay, now these equations you might have, this the first equations, at least these equations is very common to us. This we have seen in the basic soil mechanics courses, where this vertical consolidation, this TB. Okay, TB, the relation between this time factor in vertical direction to the consolidation in vertical direction, this degree of consolidation, this relation is given. Okay, this TB is given. And then for the radial consolidation, actually this UR is related to TR. Okay, TR is the same time factor in radial direction. Okay, that is given by this expression. So so actually what we'll solve a easy problem in the next this one slide. So where you will see that this UR is very easy to obtain. So the graphical solutions are actually available. Okay, graphical solutions are actually available where we have this where with respect to this what to say, this uh, time factor TR, we can get this UR value. Okay, we can get this UR value. And how to get this time factor UR TR can get by this relation CRT by D square. Okay, and what is this time factor CVT by Z square. Correct. So vertical distance, let us write is Z, vertical drainage distance Z square, so Z square. Okay, what, or you can write just, you can, if you change D vertical square. Okay, so here one more expression you can see N. What is N? N is the ratio of the radius of the unit cell area to the radius of the center. So this term unit cell, this term is actually very important. This term we will again see when we study about the stone columns. Okay, this unit cell term is actually very important. So what is the unit cell? This is actually, say you have sand grains like this in the soil. Okay, so this unit cell is nothing but the influence area of each of these. Okay, the unit cell is nothing but the influence area of each of these. This can be actually represented in terms of circular rods. Circular rods. Okay, this is the influence of this sand ring. Okay, influence area of each of the sand rings. That is the unit cell. So RW is the radius of the sand ring. Okay, RW is the radius of the sand ring, and RD is actually the radius of this unit cell. All right, D is the diameter of the unit cell. This is D, and RD is obviously half of that. All right. Now let us see this easy problem. Okay, this is just a basic problem. So embankment is proposed to be constructed over a layer of clay 10-meter thick, underlain by an impermeable stratum. Okay, the embankment is 3 meter high, and the fill soil has a unit weight of 20 kilonewton per meter. The clay has the following properties: the horizontal coefficient of consolidation and vertical coefficient of consolidation, these are known, and the vertical, this coefficient of volume compressibility, that is also given to us. Sand rails of 400 diameter are proposed to be installed in a square pattern at a spacing of 3 meters center to center. Okay. Determine the magnitude of the settlement that can be expected due to consolidation of the clay layer after 6 months of effective embankment load. So we'll see that, say if only vertical this drainage is there, how much consolidation will actually take place, and if we are introducing sand drains, then how much consolidation will occur in the, how much percentage consolidation will actually occur in the same time. All right, so first let us what can we do? First let us determine the what, the ultimate settlement. Okay, first let us determine the ultimate settlement. Okay, yeah, So just draw this. So there is a how much thick? 10-meter thick clay layer. Okay, and here it is impervious. Okay, it is impervious here, and at the top we have an embankment which is uh, 3 meter. The unit weight is given. Alright, this unit weight is given 20 meter. So what is the effective stress that this embankment is going to generate? What is the effective stress? 20 to 3 Newton per meter square. Okay, now let us find out the ultimate settlement, that this structure will ultimate settlement, consolidation settlement, this that this clay layer will actually undergo the ultimate settlement. Okay, so how can we write the ultimate as mv into delta h to, okay, delta h. Okay, so what is mv? 2.7 into 10 to the power minus 4 into h is 10, h is this thickness, into 60. So how much meters? 2.7 into the power 10, 60 is 0.162 meter. So 160.162 meter. So 162 mm. So this is the ultimate consolidation settlement, that this structure will actually that this soil layer, this clay layer will actually under. Okay, now let us come to the vertical drainage part. Okay, say now we just have vertical drainage. So in our vertical drainage, what is the drainage path, the maximum drainage path that the soil has to undergo? That is 10 meters. Okay, this is the length of drainage path. Now let us find out for vertical drainage. T is equal to C T by square. So single drainage. So what is CV? CV, what is CV? It's given 4.5 meter square per year. Okay, 4.5. What is the time we need to determine for how much? 6 months. 6 months. 6 months means what? 0.5 years. So we are putting in years, as this one is also per year. Okay, weight by each square is 10 square. So please find this out. So 0. 0.225. This is the TV. Now for less than, for degree of consolidation less than 60 equal to 60%, what is TV? Pi by 4 u square. So what is UV? Is vertical. Root over 4 by pi into equal to 0.17. Okay, this is so degree of consolidation is 0.17. All right, so only if that is vertical drainage. Okay, Degree of consolidation is 0.17. That means what? That means 0.17 times this 162. So in half a year, 0.17 times 162, that is 27.5 mm settlement is going to occur if only there is vertical drainage. Okay, if only there is vertical drainage, there is going to be only 27.5 mm settlement. How did I got this term 27.5? 0.17 times this total ultimate settlement 162, that will give me 27.5. So only 20.17 times 20 this 162, this is 20, only 27.5 mm settlement is going to occur in zero point 0.5 years, that is in 6 months, only if there is vertical. Now you will see, if there is, if sand drains are also introduced, okay, if sand drains are also introduced and if there is radial drainage also, then what happens? So what is the dia of sand drain? Dia of sand drain is given as 400 mm. It's given, okay, sand drains of 400 mm diameter. So radius of sand drain is 0.2 meter, right? Right. And one more term we want to know is that, see, RW we found out, RE is the radius of unit cell area. So say we are having square pattern of arrangement, okay, so in square pattern arrangement, so for square pattern, R is actually 0.564 into spacing, okay, and what is the spacing? It is given 3, so 1.692 meter. Okay, this is the radius of the unit cell. Okay, this is the radius of the unit cell. Therefore, N is equal to R by RT. So, what is R? 1.692 by 0.2. Okay, so N we got, small n we got. Now we want to find TR. TR. Okay, so what is TR? How to get TR? CHT by 4R square. Okay, 4R square. So remember this expression. So 8, this is given 2.5 by 4 into square. So this will come out as 0.9. Okay. Now let us come to this. For TR is equal to 0.349, N is equal to how much? What was our N? 8.46. For these values, you can, what we need to do, we need to get this UR from this chart. Okay, from this graph we need to get. So TR is how much? 0.349. So 0.1, 0.2, so all approximately here. Okay, 0.349. And N for N is equal to 8.4, means the graph is going to be approximately here or slightly below that. So just an approximate value actually we will be trying to get. Okay, it will be somewhat like this. Okay, so just approximate value, say, sorry, okay, just an approximate value, so it might be here also, just need to interpolate the value, so approximate we will get. Okay, from graph we can just get the approximate value. Okay, I'll just erase it so that later it's clear for you. So from here, so approximately, so some tables are also available. Okay, tabular solution is also available for this in some books, so you can refer to that also. So approximately UR is okay. Now how to get the average settlement? We get it. Uh, Minus how much was UV? 7. So 1 minus U is equal to how much? 7. Okay, so here you can see initially only for vertical we got only 17% percentage consolidation. Now when you are using the sand rays also 89% consolidation is actually occurring within the same time, 6 months. Before only 25 mm settlement, 20 how much, 27.5 or something like that, right? 27 point on before only 27.5 mm settlement we said that will occur in 6 months if only normal drainage is there, only vertical drainage. Now due to the introduction of this sand drains, there will be 162 times 0.89, that is 144 mm settlement will occur. So almost 90% settlement will occur within the same time frame, that is the 6 months time. Okay, so right, hence settlement of embankment at the end of 6 months is at 0.89 into 162 45. So only it is how much, so only 79 only 17.5 mm settlement is going to occur after. Okay, that means in the 6 months 144 mm settlement will occur, and just from 6 months to say infinite time only 17.5 mm settlement. So maximum settlement is 90%, almost 90% settlement is going to occur within 6 months time. Okay, so maximum settlement will occur before it. So after that what you can do, you can start constructing something over that embankment or something, whatever you want to do, so it will be actually safe. Okay. Okay, now let us come to these PVDs. Okay, let us come to PVDs. So PVDs are what? Prefabricated vertical drains. So just a what? PVDs are just the more advanced version of this sand drains. Okay, so here with the help of geotextile and coagulated plastic, we are actually manufacturing a device which is easier to install. Okay, which is more easier to install and more lasting than this sand drain. Okay, sand drains, and easier, both easier and faster to install, okay, than sand drains. But the purpose of them is also same. What is the purpose? Purpose is this drainage. Okay, purpose is same, drainage of uh, water, and then finally lead to accelerated consolidation. Okay, so if you remember, I had shown some pictures of PVD in the first session, right? So there were some where we had gone for a site visit. Those are photos I had shared. So similar photos you can see here also, where PVDs actually come in 100-meter size of rolls, and these are installed by these devices, these machines. So they are just connected to this, and with the help of this machine, they can be easily driven into the soil. All right. So typically they are 100 mm wide and 5 mm. So length is typically 100 mm, and this thickness is 5 mm, and the tensile strength is 5 to 15 kilograms. Okay. The typical discharge rate of these are 2 to 5 liters per minute, and consists of the drainage cord and a filter. So this drainage cord is there of made up of corrugated plastic. So this drainage cord is actually helps the water to travel through it. Okay, so the water will actually travel through this drainage cord, and surrounding that we actually have this geotextile filter. This geotextile filter, what is the purpose of this filter? This filter actually allows only water to pass inside the PVD. Okay, so it acts as a filter. It allows only the water to pass, and it actually does not allow the small soil particles to enter into inside the PVD. So what will happen if soil starts entering? It's gonna block the drainage path, right? Block the drainage path. So that this does not happen, this geotextile filter is actually there present around. So PVDs come in a roll of about 100-meter length, and they are pushed rapidly. So with the help of this machine, PVD rolls attached to it, easily. The installation is extremely easy. So just mark the positions and place the machine over there, and you can easily push the PVDs inside the soil. Okay, the installation is very fast and easy also. Now there are some inherent problems in centrics. Okay, and these problems are actually overcome with the help of PVDs. Okay, these problems are actually overcome with the help of these activities. So sand in the drains actually get clogged easily. So what will happen? So sand drains are there, and around the sand drains you have this fine particle soil. It's a clay soil generally. So what happens is fine particles of the clay that actually tend to clog this sand. Okay, clog the pores of the sandy column that you. So in order, so because of that, what happens? Because of that, the water, this drainage, the water drainage, the output of the water. Okay, this water output of these drains are actually reduced because less water can. There are less available pores. It clogs the pores. This fine particles will clog the pores, and hence what happens? It's very difficult for the water to travel. All right. So there is a very big problem. The second thing that happens is that continuous drainage path is disturbed due to internal shear movement. So, as you know, you have a long sand column, right? You are having a long sand column. So, what happens as you are providing load at the top? As you are providing load at the top, there are going to be continuous movement of this column, right? So you are applying load, so some shear deformations will be there on the center. So because of that, what happens? This drainage path, this continuous flow of water is actually disturbed. get disturbed due to this movement. Okay, so what happens is you are having this sand rain, right? So over that sand rains are long columns, the long columns, and over that you are applying some pressure, right? You are applying some pressure in order to increase the effective stress. So there is some loading about that. So due to that loading, this there is movement, there is disturbance, there is disturbance in this column. So there are shear movements. Okay, there are shear movements in the sand columns. Sand columns. What happens due to these columns? This continuous flow of water, the continuous flow of water is restricted. Okay, it gets totally disturbed. Alright, and also it takes a long time to install the sensor. So what you have to do, you have to drill a hole, then say you need to put some casing, or then stabilize with put some casing, then you have to put sand and layer, you have to compact it layer by layer, you have to do that. So it's very lengthy process. Fourth is the smear effect. Smear effects will actually, so what is smear effect? Smear effect is while we are installing the sand ring, okay, while we drive this channel into the soil. Okay, what happens during the installation process, the clay soil that surrounds that part, surrounds that portion, the clay soil that surrounds that portion, what happens, it gets disturbed. And disturbed is what, it gets remolded in a way. Okay, the surrounding soil, clay soil actually gets remolded. Due to this remolding, what happens, the permeability of this surrounding clay soil reduces more. Okay, it's get reduced. The, from, okay, the permeability of the surrounding soil is get reduced more due to remolding of the soil. Okay, due to the remolding of the surrounding soil, the permeability actually reduces. All right, that is actually known as smear effect. So due to this, what happens, the output of the efficiency of the sand drains get reduced because of reduced drainage, because soil is difficult, it's difficult for the soil to travel through less permeable soil, right? So what happens due to remolding, this remolding, the permeability of the surrounding soil actually reduces. Okay, and this effect is known as the smear effect. All right, so now this PVD is actually overcome this effect. So continuous flow path even after shear movement. So even some movement is there, so there is continuous flow path is maintained because of this corrugated sheet. Okay, corrugated, this core that the PVD has, due to the separate distinct corrugated core, continuous flow path is maintained there. Okay, no clogging due to geotextile filter. So as I said, we have a geotextile filter around the core, right? So this filter doesn't allow the entry of fine particles. Okay, entry of fine particles, restricts the entry of finer particles, so that the core doesn't get clogged. So there is no clogging due to this geotextile filter. And third is the reinforcement action due to the tensile strength of the PVD. So this PVD, this geotextile, and this plastic sheet, obviously that has some tensile strength, right? So what happens? This somewhat it acts as a reinforcement for the soil. It strengthens the soil by some extent. Okay, by some extent. All right. So as I was saying, discussing before also, so similar to sand rain. So see here also we have this arrangement. Okay, these are called unit cells. Okay, these unit cells where you have some diameter of influence is d. Okay, this is actually from the unit cell. Okay, and triangular pattern is always more efficient than this circular square pattern. Sorry, the square pattern. Triangular pattern is always more efficient than the square. Now Hansbow actually gave some equation where we can determine the time required this for a certain amount of so to achieve a certain degree of consolidation. Okay, by this equation, where you can see this time is related to the t, D is nothing but the influence area. CH is the coefficient of consolidation in horizontal direction. Small d is the equivalent diameter of the PVD, and U bar is nothing but the average degree of consolidation. Okay, so how actually this PVDs, how can we get the time required to attain a certain degree of consolidation that was actually given by Henslow. Okay, now let us solve this easy problem, very basic. So a PVD size is given to us 100 mm to 5 mm. Consolidation to be achieved is 70%. Time available 9 months. Coefficient of consolidation is given 10 meter square per year. Alright. So these PVDs are actually what, somewhat rectangular, right? So it has a length and it has a thickness. Okay, so what we do to get the equivalent diameter, okay, equivalent diameter, what we do? So what is the perimeter? Perimeter of triangle, 2 into length plus breadth, right? That is equated to the perimeter of a circle. So from this actually we can get the equivalent diameter of the equivalent. So this PVDs are rectangular, right? So that we are transferring into representing as a equivalent diameter. We are getting the equivalent diameter out of it, so as if it is circular. Okay, right, fine. So this will come out as 66.8 mm, nothing but 668 meters. Now we need to achieve 70% consolidation in 9 months time, right? So we need to achieve 70% consolidation in 9 months time. Okay, so let us use Hensbou's equation. Okay, so we need to, so ultimately what, so ultimately our purpose is to design, okay, so to determine the spacing and arrangement of this this PVT. Okay, so in order to achieve 70% in order to achieve 70% consolidation in 9 months time, what is the arrangement and the spacing of the PVDs that we should have, that we need to find out, right? So right, so we'll just check the equation once. Right. Okay, so let us put the values. So 9 months, so 9 by 12 years. D square, we need to find out D square. 8 CH is given 10 meter square per year. D by 0.0668, 0.75 to ln 1 by 1 minus. Okay, so let us put all the D terms in one side. Okay, how much is this? So now if you want to solve this, so this in this engineer calculators actually nowadays we can directly put the equation and get the values. Else what you can do, you can do some trial and error to get the value. So I will just directly put the equation. Okay, I will just show you. Okay, show you square into x by 0. Okay, so see, I don't know if it's visible. So like this, actually, you can write the whole equation in the calculator. Okay, it's not visible actually clearly. So like this, actually, you can write the whole equation and then try to solve for it. So from that, d is approximately coming as 879 meters. So you can take 3.8 meters. Okay, that will be safer, right? So lesser spacing will be always safer. Safer design. So spacing we determine spacing. So if you have square pattern, if you are using, then 3.8 by 1.128, and if triangular pattern, if you are using, right? So it's given here, right? So it's given here. So from here we are just getting that. So d is equal to 1.128. So s will be d by 1.128. So 3.8 divided by 1.128. 3.4 meter. Till it's 3 point not 4. Yeah, approximately 3.4. 3.8 divided by 1.5. 3.6 meters. Okay, so you can provide this spacing of. So if you are putting in square pattern, you can provide 3.4 meter spacing, and if you are putting in this triangular pattern, you can provide 3.6 meter spacing. Okay. Alright. Okay. Okay. Now we already studied about sand rains, right? Then we saw first we saw sand rains. Then what did we see? Then we saw the PVDs. Now the third thing is the uh, vacuum consolidation. Okay, so this is nothing but a more faster method using which we can achieve the consolidation faster. Okay, more faster. Okay, faster than PVDs. Just using PVDs by using vacuum pressure. Okay, vacuum pressure. So what is done is actually some vacuum pressure is applied at the top. Okay, at the top. So what happens here in the soil mass, pressure becomes less than atmospheric. The atmospheric pressure is acting upward, so that actually creates this effective stress in the soil. Okay, so due to this water, obviously if you're connect over putting vacuum pressure here, so there will be tendency of the water to drain out, right? Drain out. So using this vacuum pressure, we are providing some extra extra force, to extrude the water, and this actually accelerates the consolidation process. Okay, so uh, atmospheric pressure is used in place of external surcharge by creating vacuum in the foundation soil. Okay, so the foundation soil we are creating vacuum, and atmospheric pressure is there at the top, so this gradient actually pulls the water up. So 90% consolidation achieved in just 2 to 3 months. Main concept is the increase in effective stress without increasing total. So generally what do you do? Generally, in say you are just using sand drains, you have to provide some overburden pressure of the top of the soil, right? In say in case terms of making a soil surcharge or something like that. So in that case, the total stress is increasing, or moreover, the stress is not same at all depths of the soil, right? As we go down, the effect of that overburden actually goes on reducing. So the effect of the stress is actually not same at all depths. Okay, but all these shortcomings are actually negated by using this vacuum consolidation. Okay, we'll see that in the upcoming slides how. So reduce the pressure in the soil mass, atmospheric pressure drives the consolidation. So generally there are two methods. Okay, one is with membrane cover and one other is without membrane cover. So this is without membrane cover. Say if a soil mass, and at the top of the soil mass is say we have a thin clay layer. Clay layer is there. In that case, you can use this without membrane cover. And other method is you are putting a membrane. Okay, membrane cover, impermeable membrane cover at the top, and then you are connecting all the sand drains to this drainage pipe, and then this drainage pipe is finally connected to the vacuum pump. Okay, this is one more method. Now, as I said, let us see how this increase in effective stress actually happens. Okay, so so let the unit, so say we have like this. Okay, say this is the ground level, this solid line is the ground level, and at 1 meter you are actually having this drainage line. Okay, this drainage line. So the what? So we have this drainage line here at 1 meter level. So from 1 meter to 3, from so this part is actually sand. Okay, and this part below is actually the clay layer in which we have to do this consolidation thing. Okay, in where we have to accelerate the consolidation. This is this clay layer. Okay, the thickness of what is the thickness of this sand layer is 3 meters, and from here below, so initial water table is at a level of depth of 3 meters. So what will happen when we apply vacuum here? This water is going to rise up here to here. Okay, this is the drainage path we are making, and we are connecting. Say we have the drainage line here, and this part we are connected to this vacuum pump. So when we are applying vacuum in this region, what will happen? The water will actually be got pulled up, and water table will actually rise up to here 1 meter level. Okay, so this complete is the sand layer, and below we have clay layer, and so we will be discussing two cases. Okay, and let the unit weight be dry unit weight be 18, and let the saturated unit weight be 20 kilonewton per meter. Okay, now before the application of vacuum, let us see what is the uh, stress. Okay, what is the stress in this sand layer? Okay, first, in the first case, this is 0, this is 1, this is just the sand layer we are considering. Okay, and I consider depth z. Okay, this z varies only from 0 to 3 meter now in the first case. Okay, this is case 1, only sand. Okay, now before application of vacuum, what is the total stress at any point z? What is the total stress at any point z? P atmospheric plus gamma dry into z. So what is P atmospheric? P atmospheric, you can write 100 plus 18 into Z kPa. What is the pore water pressure? Pore pressure. Pore pressure is nothing but atmospheric pressure, Pa to 100, right? So what will be the effective stress? Total minus pore pressure. It is nothing but 18 into Z. Okay, this is before the application of vertical pressure. Now after application of vertical pressure, what is gamma B at this depth? What will happen? After application of the vacuum pressure, this water table was earlier here, right? Now it will go up to here. So what? Pa plus gamma dry into 1 plus gamma set, sorry, it will be gamma not set, gamma submerged, gamma set only, right? Not submerged, gamma set times how much? Gamma set time. So water is risen to this level, right? So this side, how much is this side? Z minus 1, gamma set times Z minus 1. So this will be 100 plus 18 into 1 plus 20 into Z minus 1, right? So it is nothing but 98 plus 20 Z. Okay, I hope this is clear. Now what will be the pore pressure at this point? So now P atmospheric is not there, right? Because you have made it vacuum. So 0 plus just due to the, so water is here now, so 1 into 10, not 1, Z minus 1 into this gamma W. So this distance is Z minus 1, this is Z minus 1. So what will be the pore pressure? It will be 0 plus Z minus 1 into gamma W. So if I take gamma W as 10 for approximation, okay. So what is the effective? P2 will get 108 plus 10Z. Okay, so you can see what is now, if there is an increase in effective stress. So what is the increase? 108 plus 10Z minus 18Z. So 108 minus 8Z. Okay, so at this level, what is the increase in effective stress? So that is when Z is equal to 1. When Z equal to 1, what is the increase in effective stress? 100 kPa, right? And when Z equal to 3, what is the increase? What is the increase? 8 into 3, 100, 108 minus 8 into 3 is 8, nothing but 84 kPa. So you can see in the sand layer with depth, this increase in effective stress is actually reducing. This is the case of sand layer. Okay, this is sand layer. This is not that important to us. The main thing is that we need to see how much increase in effective stress is actually coming in our clay layer. So let us see that now. Okay, let us see that now. That we just introduced some pages here. Okay, so now this was the ground level, this is the drainage level, this was the initial this water level, and below this we have the clay layer, right? Clay layer, this is completely clay. Now measure the Z from this distance, from here, this point, so this is Z. Now case 2, only in clay layer. Okay, so before vacuum, What is the total stress at any point here? PA plus 3 times 18. 18 was what? A dry unit weight plus Z times 20, because water table is here, right? Initial water table was here, then it will get risen to here. So initial is this one. Where into 20. So how much will it be? Okay, let it be like this only. Now what is the pore pressure? Pore pressure is this point PA plus Z into gamma W. So PA plus 10Z, right? So what is the effective? Alright, this is before application of the vacuum pressure. Now as we apply the vacuum pressure, what will happen? This water table will get risen to this level, drainage level, 1 meter. Now after vacuum, what will happen? Total stress at this point. Total stress at this point. Okay, PA plus, this is dry, so 18 into 1 plus 2 into 20 plus Z into 20, right? This is 2, so this is 2, so 2 meter, 2 meter into 20 plus Z into 20. So this is what we got, to PA plus 58 plus 20Z. Alright, what is the pore pressure? PA is not present, so PA is 0. There is no atmosphere here because we are vacuum pressure providing 0 plus water table risen to here 2 plus Z into 10, right? 20 plus 2Z. So therefore, what is the effective effective stress? This minus this, nothing but 138 plus 10. Okay, this is the effective stress, right? Effective stress after this vacuum is applied. So therefore, what will be the increase in effective stress that is happening? Okay, this was the initial effective stress before application of vacuum, and next you have after the application of vacuum pressure, this is the effective stress. So what is the net increase in effective stress? This minus this, so 10Z will get cancelled, so you will get 84 kPa. So you can see in the clay layer, as the depth is increasing, the increase in effective stress is not increasing anymore, constant with depth, right? It's constant with depth now, it's not increasing. Say we are doing say you would have done normal, so normally say you have clay, this is the sand layer, you have clay layer, and say you are providing sand drains, normally sand drains, okay, not vacuum pressure you are not applying. So what we need to do, you need to provide some overburden pressure here in order to develop some effective stress. In that case, what happens? At all the as we go down the depths, this overburden pressure, the effect of this overburden pressure will actually get reduced, right? So the consolidation is actually not actually that uniform, because the effective stress, increase in effective stress goes reduces as we go down. That is actually, that shortcoming is actually overcome by use of vacuum pressure. What happens? At all depths, the increase in effective stress is actually independent. So you saw here, the increase in effective stress becomes independent of depth. So at all depths in the clay layer, at all the depths, you have uniform increase in effective stress. Okay, as a result of which the consolidation is also uniform and faster also. Alright, so that is the main benefit of this vacuum pressure. All right. So this is the main concept and the uh, main use of this decomposition. Okay, so we don't need to have this surcharge fill. Okay, we don't need to use the surcharge fill when we are using this vacuum consolidation technique. Okay. All right. So now let us come to the just let us come to the next thing. These problems in soft clay. So what are soft clay? So if you have a very soft clay soil, okay, so you have a very soft clay soil, you want to construct something over it. So there are high chances that there will be failure. Why failure? Because the soft clay layer has very low bearing capacity, right? So there are chances of deep seated failure and excessive settlements. Okay, so what are the possible solutions? So if this soft clay layer, okay, if this soft soil layer is less thickness, okay, if the amount is less, so what we can do, we can just remove the soil. Okay, we can remove the soil and replace it with good quality soil and then compact it. That is one solution. But say if the depth of this soil is high, so that time it won't be possible to replace the soil. So then we need to choose some other techniques. So some other techniques may be piling. We discussed pre-consolidation, then maybe lightweight filled stone columns and other many other options are available. So pre-consolidation we discussed. Now let us discuss the stone columns. So what are stone columns? The stone columns are all columns, also columns. They are very rigid columns. They are rigid columns. The rigidity is provided by the granular substance, the granular this aggregate that we are using to build the stone columns. The stone columns are also constructed like that only. We need to drill a borehole, then put some surrounding this. You have to stabilize that borehole. Then you have to put stone aggregate in there, compact it with rammer. That is the easiest way of construction. Now, obviously, there are more advanced waves construction also using this vibro displacement, vibro flotation. These techniques are used. But in general, if you want to visualize how that will be constructed, that is the most easiest way. So these stone columns are 800 to 100 millimeter dia or larger. Okay, so you can have very large dia stone columns also. But generally piles. So RCC piles, if we use, these piles are actually only generally 400 to 500 mm dia. Okay, but stone columns, this dia of the stone columns are almost 2 to 2.5 times more than the RCC piles. Okay, RCC piles, these are stone columns are actually quite large. The stone columns, how do they resist the load? So, so you are having this load here. So there is a tendency that the stone column. So what happens? The load is acting downwards, right? And we have the inherent soil surrounding the stone column. So this inherent soil that is present, that actually provides a passive pressure onto that column. By virtue of that passive pressure from the native soil, this stone column actually resists the uh, this resist the vertical load. So what happens? So when we applied load, there is a tendency for long stone columns, there is a tendency that it will bulge. Okay, so there is a tendency that a stone column will bulge. So due to this bulging, what happens? It pushes. Due to this bulging, there is some passive resistance that develops from the surrounding soil mass. That passive resistance, that soil actually helps in transferring the load. All right. So here you can see three types of failure modes of stone column. So first is the bulging failure. So if we have a long stone column whose length is more than 4 times the diameter, in that case what happens? There is tendency of bulging. Okay, so in that case this bulging phenomenon occurs. Okay, then if you have very short columns on firm soil, okay, firm soil. firm soil if we have, then there is normal bearing capacity type of failure that might occur. So generally in this case, we generally do not use stone columns. What we do, we just tend to replace the soil. Okay, replace the soil because of the shallow depth. And the third case is that, say if we do not have the strong firm ground here, so this bearing kind of thing will be there. Okay, so everything our stone column is actually given in IS 15284, and we will be using this IS code to design stone columns. So one more advanced version of stone column is our NK stone columns. So in NK stone columns, what happened? We provide a geosynthetic encasement around the stone column, maybe of geogrid or maybe of geotextile. Okay, we provide some geosynthetic encasement around the stone column. So here you have the stone exhibit. So around that we provide some geosynthetic encasement. So what happens due to this encasement? Due to this geosynthetic encasement, some external additional confinement is there. Confinement pressure is there. So we'll see how to calculate that additional confinement pressure. So additional confinement is there. So because of the additional confinement, what happened? The capacity of the stone column increases. All right. So if you see this figure here, first we have the homogeneous clay, that is, then we have the ordinary stone column. Okay, then we have the semi-rigid stone, this encased stone column. Okay, that is semi-rigid. Okay, then you have the pipe, that is the most rigid. Okay, so these are the various solutions. So here a short diagram is shown how these encased stone columns are generally constructed. Okay, so advantages of encasement: imparts lateral confinement. As I said, there is extra confining pressure. So due to this confinement, the load capacity and stiffness of the stone column increases by many-fold. Stresses are can be transferred to deeper strata. Higher lengths of stone column is possible. We can make construct higher length of stone column. Lateral squeezing of the stone is prevented. Higher degree of compaction can be achieved. Prevents the clogging of stone columns, and strength properties of the aggregator preserved. Okay. So these are some of the advantages of using encasement. Now, as I said, what happens due to the uh, use of this encasement, there is some extra confining pressure. Okay, there is some extra confining pressure. Okay, there is extra confining pressure that develops. That was given by Henkel and Gilbert. Okay, this extra confining pressure was actually derived using this Henkel and Gilbert equation. So they actually derived this equation for confining pressure for a membrane. Okay, so that concept was again used for stone columns also. Okay, so confining pressure in the membrane due to this encasement is given by delta sigma 3 is equal to 2 m by epsilon c by d into 1 minus epsilon a. So where this epsilon c is actually the radial strain that develops in the encasement, and that radial strain can be related to the axial strain by this relation. Okay, so the additional axial capacity is given by delta sigma 1 is equal to delta sigma 3 into the k into kp. Kp is nothing but the coefficient of passive pressure. Okay, and you can see this term m here. M is the second modulus of the confining membrane, or the confinement geosynthetic that you are using. That is the second modulus of that. Okay, okay, just a second. So this is actually the limiting stress of the ordinary. You will see the code that will clear, and here we discuss due to the encasement what is the additional confining pressure we can get like this. So encasement is more effective in lesser diameter stone. So these are some results that were obtained experimentally by doing large number of experiments by many researchers. So they actually drew these conclusions. So encasement is more effective in lesser diameter stone columns because of mobilization of larger confining stress. Okay, significant improvement can be achieved by encasing the top portion to depths of 2 to 3 times the diameter. The load capacity of encased stone columns is not as sensitive to shear strength of the surrounding soil as compared to OSCs. The magnitude of load transferred into the encased stone columns of the embankments can be increased using stiffer encasement. Okay, so if you use stiffer encasement around the stone column, you can increase the magnitude of load transfer. So you can increase the load carrying capacity. Now let us see this. So these are the excerpts from the this IS code IS 15284. So let us just see this a little bit, okay, in detail slowly, because this is very important. So first here you can see something is mentioned about, so all these things actually we will be needing. Okay, that's why let us just go through all these things whatever it's mentioned in the code here. First is the equivalent diameter. Okay, so what is the equivalent diameter? Equivalent diameter of what? The equivalent diameter of the tributary area of soil uh, surrounding is stone columns from regular hexagonal. It may be closely approximated by equivalent circular area having the same total area. Okay, as represented here. Okay, so there are two arrangements possible as we know: triangular arrangement, and other is the square arrangement, right? So the diameter of these equivalent circles in both this arrangement is given here. So for triangular arrangement, we have the equivalent diameter is equal to 1.05 times S, right? This 1.05 times S. And for square pattern, we have 1.13 times S, where S is the spacing of the stone columns, right? So this is about the equivalent diameter. Next important thing is the replacement ratio. So what is the replacement ratio? So what we are doing, we are some amount of the soil, some amount of the soil in the complete unit cell is covered by the stone column, right? So this is the unit cell. So here in the unit cell there is soil and there is the stone column, right? So there is a term known as replacement ratio. The replacement ratio is nothing but the area of stone column divided by the total area of this unit cell. Okay, so you can see AS is the replacement ratio is equal to AS by A, where AS is the area of the stone column and A is the total area within the unit cell. The total area of the unit cell is nothing but AS plus AG, where AS is again the area of the stone column and AG is the area of ground surrounding the stone column. That means this ground, this portion. Okay, okay. Yeah. The area replacement ratio may be also expressed in terms of d by s. This is the diameter to spacing, that is, and this coefficient constant 0.907 actually is a function of this arrangement. So for triangular arrangement, it is equilateral triangular arrangement. It's 0.907. Okay, so equivalent diameter, we learned what is equivalent diameter, then we understood what is replacement ratio. Okay. Now let us come to this load capacity calculation. So the first is capacity based on bulging of column. So as I had mentioned, what will happen? There is a tendency for the soil to the column to bulge. Okay, so due to the bulging, there is a passive resistance that develops from the surrounding soil. And that passive resistance actually helps the resist the load. So capacity based on this bulging of column. Okay, so this stone will be actually pushing this into the soil. So that into that this passive resistance actually develops. So you can see here this vertical limiting axial stress in column here, this one limiting axial stress in the column when it approaches shear failure due to bulging is given by sigma v. Sigma v is nothing but sigma rl times kp of the column. Kp of the column means the passive coefficient of the column. Okay, passive earth pressure coefficient of the column, and sigma RL is the limiting radial stress. And what is the sigma RL? The sigma RL is given by this sigma RO plus 4Cu. Okay, and in this, what is the sigma RO? Sigma RO is the initial effective radial stress. It is nothing but K naught times sigma V naught. What is K naught? K naught is 1 minus 1 minus sine phi. Okay, 1 minus sine phi. That is the your what to say? Uh, Earth pressure at rest coefficient of the soil, okay, of the soil 1 minus sine phi, and sigma v naught is nothing but gamma times twice d. So twice d is d is the diameter of the stone column, okay, 2 times the diameter of the stone column times gamma. Okay, so everything is actually detailed in the code. So finally we can get the sigma v like this. Okay, so after we get the sigma v, after we get sigma v, what we can do, we can determine the safe load on column q1. So q1 is equal to sigma v into the area of the column. It is equal to pi by 4 into d square. D is nothing but the diameter of the stone column. Okay, remember d is the diameter of the stone column. Now if our soil is say C5 soil, they say our soil has some friction angle. So this was for just for cohesive soil. Say the soil is just completely cohesive soil. There is no phi value. Okay, now say we have a soil where we have this phi value also. Okay, along with the cohesion value we have the C value. So initially that was only for the soil with C value. Now say we have in soils having both C and phi, both cohesion and your friction angle. In that case the passive resistance is given by Bell's formula, the sigma RL, which was initially previously given by this, which was previously given by this, okay, is now given by this, where when we have also phi is available. Okay, and other things is it everything is same. Okay, all the other things are detailed there, the other things are same. So sigma RL will change if we have phi also in the soil. Okay, all right. Okay, this was capacity based on the bulging of column. Okay, whatever capacity is there because of the bulging of column. Now next is there the surcharge effect. So what is that? The surcharge, initially the surcharge load is supported entirely by the rigid column. As the column dilates, some load is shared by the intervening soil depending upon the relative rigidity of the column of the soil. The consolidation of the soil under this load results in an increase in its strength, which provides additional resistance against bulging. So it is clear, straightforward. So what happens? Column is there, okay, column is there, and surrounding the column this soil is there, right? We have the stone column, and surrounding the column we have soil, and above this we are providing some surcharge load or the whatever load is acting. So initially what happens, initially this surcharge load is carried immediately by the stone column. Okay, then what happens due to the dilation of the column. So what happens, load is acting, so there is some dilation of the column. Okay, there is some dilation of the column. Okay, there is some dilation of the column. due to the dilation of the column, some part of this load transfers to the surrounding soil around this surrounding soil around the column. So this transfer actually depends upon the relative rigidity of the column in the soil. So how relative to the soil, how more rigid is the column, or how less relative to the column, how less rigid the soil is. Okay. So some load gets transferred to the surrounding soil. So initially, immediately the column is taking. Then what happens? Like there is this what to say dilation of the column. To that, some load is transferred to the surrounding soil. So due to this transference of load, was when the consolidation of the surrounding soil happens. So as the consolidation of the surrounding soil happens, uh, uh, the strength of the soil actually increases by some. Okay, and this increasing strength of the soil provides additional lateral resistance against this bulging. Okay, that we are about to calculate here. What is this additional resistance about this effect, surcharge? Okay, so the increase in capacity may be calculated by this q safe by 3 1 plus twice cannot q safe by 3 is nothing but the this safe bearing pressure of the soil. Okay, and is given by this. It's given here safe by 3, and then finally we can get the increasing load q2 is equal to kp column, which is the passive earth pressure of the column, times the this r naught times as. As is the area of the stone column, pi by 4 d square, area of the stone column divided by 2. 2 here is nothing but 2 is a factor of safety here. Okay, so with this we can calculate q2. So we got q1 from this pairing, this one bulging column effect, q1 you got, then we got q2 from surcharge effect, then next is the q3. q3 is nothing but the bearing support that is provided by the intervening soil. Okay, this is the stone column surrounding soil, the being the bearing, the inherent bearing capacity of the soil, whatever that is providing. Okay, the inherent bearing capacity of the soil, whatever that support it is providing. So as it is written here, the component consists of the intrinsic capacity of the virgin soil to support a vertical load, which may be computed as follows. So it's nothing but Q save into Ag. And what is Ag? Ag is nothing but the area of the surrounding soil. So what will be the area of the surrounding soil? That is nothing but unit cell area minus the area of this stone column. Right. So what will be the area of this region? Total area of this region. Unit cell area minus this area. Right. That will give the area of the intervening soil. Right. So that is given by Ag. So Q safe times Ag will give us Q3. Alright. Now, as you know, the spacing and everything, we will determine. So triangular pattern, the area of each column is given by 0.866 s square, and for square it's given by 1 s square. So for triangular, you can see the area of each. This is the area of each unit cell. 0.866 s square. That is the area of the unit cell. Now, settlement reduction ratio. So this is also given in the same IS code. So what is settlement reduction ratio? Settlement ratio reduction ratio is the ratio of the settlement of the treated soil to the settlement of the untreated soil. So obviously, due to the use of this stone column, the settlement of the soil is going to reduce. So that how much reduction is happening, that is actually given by the settlement reduction ratio beta. And this beta is related to two factors. One is N and another one is AS. So AS is nothing but the area of the replacement ratio. Okay, this AAC is nothing but the replacement ratio, and if you remember, we had discussed the replacement ratio, right? So this AAC is nothing but this replacement ratio, and N is the stress concentration factor. Okay, so what is the stress concentration factor? Let us see. Stress concentration uh, concentration occurs on the stone column because it is considered, so obviously the stone column is quite stiffer than the surrounding soil, right? Okay, the stone column is quite stiffer than the surrounding soil. So because of this, stress concentration will occur on the stone column. So stress concentration occurs on the stone column because it is considerably stiffer than the surrounding soil. From equilibrium consideration, the stress in the stiffer stone column should be greater than the stress in the surrounding soil. Alright, obviously. The stress concentration factor is given by N is equal to sigma S by sigma G. What is sigma S? Sigma S is nothing but the vertical stress. Come here, vertical stress in the compacted columns, and sigma G is the vertical stress that is taken by the surrounding soil. So this stress concentration factor N is generally lies between 2.5 to 5. Okay, generally lies between 2.5 to 5. So stress concentration factor may be predicted using the elastic theory as a function of the modular ratio of the stone column of the clay, assuming equal vertical distance. So modular ratio, what was the modular ratio, means nothing but the ratio of this ratio of the elastic modulus, I think. Okay, or I forgot. We studied this is a, we might have, if you recall from the basic solid mechanics class, if you recall modular ratio. So this stress concentration factor can also be predicted using this modular ratio. All right, so generally this modular ratio varies can vary in certain factors. So generally the stress concentration factor N is taken between 2.5 to 5 depending on how stiff the this stone column is with respect to the surrounding soil. All right, now let us come to this problem which was given. So the area to be treated consists of a soft clay with undrained cohesive strength Cu, of 40 kPa. Okay, 40 kPa, and the thickness of the clay layer is how much? 10 meter thickness. The thickness of the clay layer is 10 meter. The assumed diameter of stone columns is 800 mm. The applied pressure on the soil is 150 kPa. Friction angle of the stone aggregate may be assumed as 50 degree, K naught as 0.5. The total treatment area is 90,000 meters square. Estimated number is 2. So let us see how to solve this. So to solve, we will just follow the steps given by the IS code. We already discussed the step. We'll just follow the steps. Okay. First, the ultimate bearing capacity of the soil. Okay. Nothing but NC into C. 5.14. What is C? 40 kPa. So what is the safe bearing capacity? So 85. Okay, now three parts are there, right? Q1, Q2, Q3. Now first let us determine Q1. Q1 was what? Capacity of stone column based on bulging. What was Q1? This was Q1. So in that Q1, what was Q1? Q1 was sigma V times pi by 4 into diameter square. Now what is sigma V? Sigma V is sigma RL times Kp column. What is sigma RL? Sigma R naught plus 4Cu. What is sigma R naught? So let us do one by one. First, let us find out sigma R naught. Sigma R naught is K naught times sigma V naught. K naught is 0.5, and what is sigma V naught? Gamma times 2T. So 0.5 times 10, assuming effective unit weight is 10. Okay, effective unit weight here is assuming 10 times your twice t. So 2 into 0.8. So 800 mm diameter means 0.8. So this will come out as 0.5 into 16. So 8. Okay. So now we can get sigma RL as 8 plus 4 into Cu, 4 into 40. So 160 kPa. Okay. Now what is sigma V? Sigma V is sigma RL into Kp column. What is Kp column? 1 plus sine 50 degrees. This is the phi of the aggregates that you have used to meet the stone column. Sorry. Array. This will come out as 7.55. So 160 times 7.5. Okay. So therefore, finally, what is Q1? 1, 2, 6. 1268.4 times pi by 4 into 0.8 square divided by factor of safety 2. Okay, this is factor of safety 2. So let us find this out. 1268.4 times pi by 4 square 318.8. So this one you got Q1. Now next was what? Next was the surcharge effect. So due to the surcharge effect, what is the additional confining stress that is coming? Q saved by 3, 1 plus 2 by K naught. So what is Q save? 85 by 3, 1 plus 2 into 0.5. Come out as 56.7 Kp. Therefore Q2 Kp column to a column to 7.55 times 56.7 times pi by 4 into 0.8 square by 2, this will come out as 107.6. This is Q2. Now next is Q3. We need to find Q3. For Q3, what was Q3? Q3 was Q safe into Ag. And what is Ag? Ag is the area of intervening soil. So it was 0.866 s square minus pi d square by 4 in case of triangular pattern. And in case of square pattern is this. Right. So Q3 will be nothing but 85 times Ag. Now finally what we do, we need to determine the spacing, right? So total Q you got Q1 plus Q2 plus Q3.
total Q we got. This we will equate to the total pressure that is coming, that total load that you have to reduce. So 150 kPa is the applied pressure on the soil. So that load actually we have to resist, right? So we'll equate this to that and find out the spacing. So for triangular pattern, okay, here there is a thing I would like to discuss. Just a second. Just write everything with red only. 0.503 is nothing but pi by 4 into 0.8 square is equal to 150 times. So whatever solution that has been provided in this one, okay, in NPTEL, I saw that they have done this they are multiplying by this AG. But what I think is that, personally what I think is that, what I think it should be 150 times 0.866 square, because it's acting on that. You are doing all the calculations per unit cell, right? Why are they just taking the area of this intervening soil? They must have should have taken this complete area of the thing. So I what I should it should be what I think it should be this. Okay, so please verify it from the course instructor. Write it clearly. Okay, so please verify this from the course instructor. Okay, so like this, just you can solve this and find out s from here. In case of triangular, so what they have got is, for triangular they have got s as 2.86 meter, and for square this is for triangular, and square they have got 2.65 meters. Okay, so now what we can do, we can determine the approximate number of columns. Triangular, it will be 90,000 is the area, divide by 0.866 times 2.86 square, it comes at 0.05, and for square pattern it comes out at 90,000 by 1 into 2.86, 2.65 square, just 12,815 columns. Okay, like this. So please just verify this. Whatever I think, personally think, it should be 0.86 is s square. This right hand side 150 should be multiplied with 0.86 is s square in case of triangular arrangement. In case of square arrangement, it should be multiplied with s square only. So this term should not be there. Okay, 0.503, this term should not be there, because why are you deducting this? This is acting on the complete unit cell area, right? So we should take this unit cell area. So please verify this from the instructor. So I am not doing this, just to verify this. And one more thing, in the solution that they have provided, the settlement ratio that they have done, in determining the settlement ratio, they have done this n, they have found out as sigma stone column by sigma soil. Okay, and it is coming out as approximately 19.92. So I don't think this is correct. see this, as I already discussed this before, right? So if you see here also, the stress concentration factor should come between 2.5 and 5, right? Should be between 2.5 to 5. So whatever they have calculated here, I don't think that is correct in the NPTEL solution that they have given. So please speak with the course instructor regarding this also. 2.7.6.2, right? Okay, please verify this from the course. Okay, so this was an ultimate total load carrying capacity. What they have found out in case of a triangular arrangement is how much. So total load carrying capacity, just put the value of S here, 318.8 plus 107.6 plus 85 times 0.866 into 0.86 square, yes, 985 kilonewton. This is in case of triangular, and in case of square they have calculated this as 980 kilonewton. Okay, now what will happen if we provide the encasement? So due to the encasement, additional uh, this additional confining stress will be acting on it. So what was the additional confining stress? Right, so what is d? D we know, d. Okay, and let us assume actual strain as 5%, and say we are using a geosynthetic, second modulus of the geosynthetic is 5, right? Kilonewton per meter. So let us find out what is the additional 2 into 500. Okay, this comes out as 33 kPa approx. Okay, 33 kPa approx. So, and this sigma 3 will actually be added to what? It will be actually added to this sigma RL. So this sigma RL will now become sigma R naught plus 4 this was already present, plus this sigma 3 into, okay, sigma 3. So this sigma RL will be now how much? So initially what was that? How much sigma RL was there? Let us see. 160 kPa. So with this 160 kPa, this 33 will get added. So it will be 193 kPa. Okay. Therefore, Q1 will now change to sigma RL. So this is sigma RL. So what will be sigma V? Just a second. For that, I have to be able to say sigma V is 160, not 160, right? 4 into 40 plus, what was not 8, 168, that's right, no? 168, 168 plus 33, 201. So previously the sigma model was 168, 168. So I made the mistake here, right? So it should be 168. Okay. Two zero one kPa. So 201 into 7.55. 20, sorry, 1517.55 kPa. Therefore now Q1 is becoming 1517.55 into pi by 4 into 0.8 square by 2, 381 mu Q. So previously how much was Q1? Previously Q1 was 318.8 kilonewton, right? 318 kilonewton. Now it has increased to 381 kilonewton. So previously it was, so now if you use more stiffer, so more strength, this M, if you now decide to use a geosynthetic of higher second modulus, okay, more stiffer, okay, then you will see that you are getting higher this capacity, higher Q1, more higher Q1. Okay, you will be getting higher Q1. All right. Okay, so this was all about it. Just follow whatever is given in the code and solve the problems, and also please discuss the concerns that were, if possible, please discuss these concerns that were uh, raised by me. Okay, and one more thing is that say now you have a soil. Say now you have a soil. Uh, just a second, let's open it. Say now you have a soil of C, some C value 40 degree, and say it has some phi value also, say 20 degree with it. Okay, then what will happen? Then this sigma RL, this phi RL will change again. So how that will change, that I already uh, gave you. I'll just write it down. Say you have a soil of C is equal to 40 and phi is at 20. Okay, then the sigma RL will now be gamma Z
S2IC.
Now, okay, now what you have to do? You have to use this formula for calculating RL. Okay, because you have some phi value with it. So now what we need to do? You need to use this. Okay. So please see please go through the code one. So all the details are actually distinctively properly given in the IS code. So what I suggest is that just if you want to understand this design of this stone column, so what I suggest is that just go through the code once, everything will be crystal clear to you. Okay, so just to summarize, we first studied the sand drains. Okay, we saw how sand drains help in accelerating acceleration. We also solved one problem regarding that, and we saw that how with the help of sand drains we are able to achieve higher amount of consolidation in the same amount of time, right? Then we studied how to design the arrangement and spacing for PVDs. We saw what is the use of what are the use of PVDs and how PVDs help us in accelerating consolidation. And then we also solved one problem where we designed the PVDs. Then third, we saw what is the use of this vacuum consolidation and how this vacuum pressure is beneficial to us. So with the use of this vacuum consolidation, what happens? We are able to get better, faster consolidation, 90% consolidation in 2 to 3 months. And moreover, due to this vacuum consolidation, we are able to get a uniform isotropic increase in this effective stress. And due to that, we are going to get more uniform settlements. Okay, settlements in the soil. Okay, that was the benefit of this vacuum consolidation. So we also calculated, we did some rough calculations, and we saw that this in the clay layer, our at all depths the increase in effective stress was actually about constant. Okay, so we are just putting vacuum, making use of the atmospheric pressure in order to induce effective stress so that this consolidation happens, right? And then the fourth topic we discussed is that was of the stone columns. We saw what are stone columns, why they are used, how they are made, and what are the uh, uh, different failure modes of stone columns. Then we saw what are encased stone columns and how encasement of stone columns actually help in increasing the load carrying capacity of the stone columns. That we also saw. In the end, also I said that how can we find out the how the load gets affected, load carrying capacity gets affected if your soil is actually C5 soil. Okay, I will just write it down, read yourself that you can do this. Okay, so with this we will end today's session, and in the next session what we are going to do is that we are going to discuss this uh, other things that include your this designing for drainage and filtration and other purposes, other short small purposes of geosynthetics. So we will solve some short problems, easy problems regarding that so that this you can design for the drainage and filtration using any geosynthetic. So mostly for drainage, what we will do? Drainage we will be using mostly geotextile and geonets, and for filtration mostly we will be using geotextile only. Okay, so we will see how to solve that problem. So very easy problems we will be solving, and let us see what we can do. Okay, so with this we will end the ninth session. So let us meet in the next 10th session. It will be next week, that is on, I guess, on 3rd of October. Okay, so with this we will end. Thank you for attending, and have a very good evening. Thank you.
Thank you.